Good evening, students. I'll start with the class. In the previous class, we have started with a new chapter, this thermodynamics. We had seen what is thermal equilibrium, thermodynamic equilibrium, then zero law of thermodynamics, and we had seen the internal energy concept. So we know that if you have any system, okay, you fill up a gas in that. There is suppose a piston. Maybe it was here first. Okay. Then what you do, you apply some weight and put some pressure on the gas. And that pressure is called P, and this must be the area of the piston. And it's in that we can also supply some heat externally. Now my aim is to increase the heat of this gas. So we had seen there are two ways the total heat can be transferred. Okay. The internal energy can be increased in two ways. One is by providing this heat, one is by doing some work on it. Anytime you do any work on a system, okay, its energy or the heat will increase. So first law of thermodynamics says that okay, there are two ways to increase the heat. I told you, one is by increasing the internal energy or by doing the work. According to first law of thermodynamics, it states that the quantity of heat absorbed by the system is equal to the sum of increase in the internal energy by heat supplied and the external work done by the system in the surrounding. Basically, it means this delta Q is nothing but this means internal energy. U is for internal energy we had seen in the previous class, and this was for work done. Is the sum of the internal energy and this. And delta Q is heat supplied. So the total heat supplied to this particular gas, now system is the gas here, can be done in two ways. One is by applying some heat, okay, and then what will happen, I told you, these molecules will gain up this heat and then transfer to each other, and then its own internal energy will increase. Every molecule has its own energy due to its movement, that we had seen kinetic energy plus internal potential energy due to the intermolecular forces. And then this is one part because of this also, plus what is happening, there is one piston which is trying to do some work on this, so there's some pressure applied, okay, so the molecules will come closer, the forces will increase, and then again that also will lead to rise in the energy. Work is also nothing but form of energy only. So two ways, so total heat will be internal plus the work done by the piston. The same diagram actually. You draw and keep for this one only. The piston has moved to a certain distance. We'll keep it as dx. This I told you is pressure. And this is area. How much area it is in contact with the gas. There is external heat supply. Okay. Consider a system that is a gas contained in a cylinder provided with movable piston. Now, in this, what they are trying to say is, now, what is going to happen is, now the gas, this heat is being provided to the molecule. So what is happening is, as it gains the heat, the gas will try to expand. Okay. Now, if there were no two ways this can be done. One side is this way. Suppose there's a pressure, and then you can increase the internal energy. Now, what they're trying to say, this heat supplied is this energy plus this. So now, the moment you supply the heat, these molecules will gain some heat, so they will expand. Okay, in your own words, you can write, when heat supplied, gas expands. So what is going to happen is, now this gas will rise, so it will move the piston upwards. So what is happening? The gas is doing this work. The gas does the work in moving the piston. Now, who is doing the work? The gas is doing the work in moving the piston upwards. It is doing against a pressure. Now, there was a pressure which is that, but still, like, this piston is trying to push the gas down, but since it is getting the heat, so it is getting the energy to push it upwards. Okay. Therefore, work done by the system against a constant pressure. So there's a constant pressure which is coming from the piston. You know that work is nothing but force into displacement. Work done is force into displacement. Displacement is what? dx. Force can also be written as pressure into area, because force is what, or pressure is what, force upon area. You know this formula, pressure is nothing, force per area. So what will be force? Pressure into area. Reduce the letters P, area is A into dx. You know that length into breadth into another distance would always give you volume. Length into breadth is area, or breadth into height is area. So three lengths if you are multiplying, obviously it becomes volume. So area, and then this is like the height. Okay, so dx. So this whole thing will become volume. That is delta V we can. Because dx is there, that's why delta V. You just put it in equation 1. The main formula, what was the main formula? Delta Q was delta U internal energy plus work, which can also be written as, instead of delta W, okay, in terms of pressure if you want to write, then it is P into delta. Both formula are correct. This is U. Instead of work, you can also write P into delta V. Both are correct. Suppose if you know straight away the work, you can use this formula. If you know the pressure and the volume, you can use this. So two ways you can write the first law of thermodynamics, either this or this. Now, there are two types of specific heats of gas. One is at constant volume and one is at constant pressure. Don't write as of now. I'll just give one at constant volume and the second one is at constant pressure. So what basically it is done is to keep a constant volume, they fix this fixed piston. It cannot be moved. Now it cannot move means now there is heat supplied. What is going to happen? The volume, this space which is there inside, obviously is called as a volume, and there's a gas filled in this. Okay, so now if the piston is fixed, what you are basically doing, you are trying to keep the volume constant, and now you are checking what is happening to the internal energy. Okay, how much heat is needed to rise the temperature. Now my aim is to heat up this gas. So how much heat do I need to increase the temperature of this gas? So we have to check that specific heat at constant volume. The second case is where you try to keep constant pressure. Means even if the gas is rising, this is movable only, but what you try to do is you try to keep a constant pressure. This pressure you are not changing. Volume might increase or decrease. Okay, this might go up or down. This is movable, but starting initially what pressure we had put on this piston, that will remain the same, that will not change. So under that, so this is constant, volume might increase or decrease. So under this also they check what happens, how much heat we need, okay, to increase the temperature. So two cases, one they keep the volume constant and check the temperature. At one point they keep the pressure constant and check. So based on this two definition, first one is molar specific heat at constant volume. If you write, I'll write the definition. If you read, it's automatically understood. Just read and see then. It is defined as the amount of heat, how much heat you need required to raise the temperature. We want to increase the temperature of the gas, suppose, of 1 mole of gas. If there was no molar, no, then it is used in terms of grams, 1 gram of gas. But gas normally we cannot count, mostly we don't say 1 gram of gas. So we use moles because number of particles present in the gas. For solids and all, you can always, or even liquids, you can tell in terms of gram. For gases, we normally use molar, 1 mole of gas. Based on that Avogadro's number. So that anyways in detail we don't need. Only what we need to know is how much of this you need to increase 1 mole of gas through 1 degree Celsius at constant volume. If you are keeping the volume constant and then checking the temperature, it is called molar specific heat at constant volume. So basically, suppose if this was at 27 degree, I put 1 mole of gas inside and I want to make it 28 degrees Celsius. From 27 to 28, just 1 degree I want to increase it. So how much heat I will need? That is called as the molar specific heat at constant volume. Same way, second one, same definition, only instead of volume it will be pressure. And this is denoted by CV. Specific heat denoted as CV. Because V is for constant volume. Next one is at constant pressure. It is denoted by CP. Same thing you write, it is defined as the amount of whatever at constant pressure. Just repeat everything. And just write the last word as constant pressure. So if you are increasing the temperature by 1 degree by keeping constant volume, it is called CV. If you are keeping pressure constant and checking the temperature, then it is called Cp. Now we will see which is more. Cv is more, Cp is more. Cp is greater than Cv. Why so? Try to understand this. Cv, you know, I told you, I explained. This you are keeping fixed. For constant volume, piston is fixed. You are supplying the energy. Now, the only duty is now what is happening, the piston is not moving, nothing. This heat is utilized, is used only what? In heating the molecule. There is no work done, nothing. Is there any external work done now? No. Because this is fixed, this is not moving, no external work has been done. So the only duty of the fire or whatever heat you are providing is to heat up the molecule. That will be less, that much only is needed. So this will get heated up faster, quickly, because only this much is done. But under constant pressure, now what is happening is this is movable. So it needs to maintain that constant pressure. Now what is happening? There is some pressure. How much ever it may not change, but there is pressure. Some pressure is there from the piston on the gas. Now what the heat will do? This will start expanding. Now there is some external work. First it has to, it has to maintain that external pressure. So there is an external pressure also on the gas. So it was maybe compressed. Now first it has to expand. So there is some work done also against this external pressure. Plus then it has to increase the internal energy. You have only one duty, no work done. So zero work. Okay, so only duty is to increase the internal energy. So no work. So only here. So this way is less, no? Here you will need heat to do some work against this also, and then to increase the internal energy also. So that's why Cp is always more than Cv. So this will be less, will be more. Okay, you can just write at constant pressure or at constant volume. You can say when gas is heated at constant volume, all the heat supplied is used to increase temperature of internal energy of the gas. When gas is heated at constant pressure, what is going to happen? The gas will expand now, because Here there is no point of gas expansion and all, because the volume anyways it has no space for it to expand. Now here, because this is anyway not moving, here this is moving, so it is having the freedom to expand, because there was the pressure first, it was compressed, now it has to expand. The gas expands. So therefore heat supplied is used in two ways. Now two ways. First one is to do work against external pressure, and second one is to increase the temperature of internal energy. You can see that written. To do work against external pressure, and the second one is to increase the temperature of this aura, temperature or internal energy of gas, or it is to increase the temperature or the internal energy of the gas. Means if you are it's the same thing, internal energy of gas increasing means its temperature is increasing. So that's why Cp is more than Cv, because here two things you have to do, here just one work. So very little is enough to increase the temperature. Here you need more heat, because it has double work. Now what is the relation between Cp and Cv? The relation is given as Cp minus Cv is nothing but R. Cp, you know what it is? That is at constant pressure, specific heat capacity. This is specific heat capacity at constant volume. R is nothing but a gas constant. So this is the relation between this, and also called as the Mayer's formula. Also called as Mayer's formula. Mayers. There's a small derivation for that. Consider 1 mole of gas now. Ideal gas you can take. Now what we'll do, you have to heat the gas to raise the temperature. Now if you are raising the temperature, it will change. So let it be delta T. Change in temperature, so that is delta T. By first law of thermodynamics, first law of thermodynamics is what? Delta Q is nothing but I told you this. Either you can write it as delta W or in terms of pressure and volume. Since we are doing Cp and Cv, we'll have to use this. There's no point writing delta W and keeping, because we are trying to find relation between volume and pressure. So first case we'll see case 1 at constant volume. Constant means what? The volume is not changing. There is no change in the volume. If it was 1 meter cube before, later also it will be 1 only. So final minus initial will be anyway 0. We know that at constant volume, delta V is 0. So put this in equation 1. P into 0, no? Is only equals to its internal energy. Total heat supply will be only internal energy. We had seen that also. Only one work it has to do. It has to just raise the temperature of the gas. Work will be 0 because piston is fixed. What is specific heat capacity? Specific heat capacity formula we have studied earlier also. P is nothing but delta Q upon delta T. There's some constant also. Constant is not to be considered. The main thing in terms of molar, then there is nu. That anyways we are not using. Nothing but change in heat with change in time. Not time, sorry, temperature. This is your overall this what is that specific heat formula. But at constant volume, what we'll do, we'll just use the letter V. This is a general formula, but since we are doing it volume, so we'll just use the letter V. What is delta Q? Just put it there. Just put delta Q equals to this one. Mark this as equation 2. Cv is nothing but delta U upon delta T. So this was at constant volume. Now we'll see case 2 at constant pressure. Constant pressure. This will not become 0. This is not delta P for it to become 0. Change in pressure would have become 0. Okay, if this was delta P, this would have been 0. But at constant pressure, it will remain, it can't become 0. So they are not minusing anything. Here volume we were minusing, final minus initial. Delta V means change. So that's why change was becoming 0. So at constant pressure, the same formula will remain. Okay. This is constant. Will not become 0 again, I'm repeating. Now what is this? Same how we had used no specific heat capacity or Cp will be, we'll just use the same formula, it is delta Q upon delta T, only at P we will use. Now put this delta Q over here. What is delta Q? Delta U plus P delta V. Now just distribute this delta T to both the places. Cp equals to, I just distributed delta T to both the places. Now look at equation 2. What is delta U plus delta T? Delta U plus delta T is nothing but Cv. From where did I get? From equation 2. Now just take Cv on the other side. If your teacher doesn't do this derivation, you can skip. Okay, but we need something R over here. This part we have got Cp minus Cv. Now we are doing for ideal gas constant. So we know that for 1 mole of ideal gas equation and the thermal properties of matter I have given to you all. Pv is nothing but, you know that, mu RT. You can go back and check also. Now 1 mole means this will be 1. So for 1 mole, mu is 1. So therefore Pv will be RT. So we'll just take derivative on both the sides. So that will be with respect to T. So PV, delta PV upon del, I'll write on top. Delta both the sides with respect to delta T. Now whatever is constant will always come out of the derivative. Over here what is P is constant. Under constant pressure we are doing this second case. P will come out. R is also gas constant. R will also come out. This you can mark as equation 3. And what is it? Just put the value of equation 3 here. What is P delta V upon delta T? Nothing but Cp minus Cv. And this is R. So from 3. So Cp minus Cv is nothing but the gas constant R. It's something called as thermodynamic state variable. an equation of that state. This thermodynamic state means at the equilibrium state. So any this thermal equilibrium, any state is dependent on, okay, you have to describe based on what. When we say any two things are at equilibrium, when temperature of TA will be equals to TB, then we say these are at thermal equilibrium with each other. Same way, we had seen there could be pressure involved, there could be volume involved, then they change P1, V1, P2, V2. So all these are described. This thermal equilibrium are described based on many variables. These are called as variables, or called as also macroscopic variables, which are given in the previous class. So they are nothing but pressure, volume, temperature, mass. The equilibrium state of a thermodynamic system is described by some specific values, specific values of the state, also called as macroscopic. That is, which all are the variables, which are the thermodynamic state variables: pressure, volume, temperature, mass, and composition of the gases. This is in case of mixed gas. If it is a single gas, then only these are needed. And the equation is of an ideal gas would be PV is equals to mu RT. So we know that under constant pressure or constant volume, what can be this? Only there can be two independent variables under this. So which all are the variables here? These are constant. This is constant. This is also constant. Because R is a gas constant, this will be normal. How many moles? What changes is variables mean nothing but it is varying and changing. What can change? Pressure can change, volume can change, or temperature can change. So the two independent variables could be pressure and temperature, or it can be pressure and volume, and temperature and volume. Like that you can change. One you can keep constant, the other two you can change. That way. You can make them independent of each other. And if you try to plot a curve, no, any this graph and all, pressure volume curve. Suppose if you want to plot pressure versus volume, if you keep temperature fixed and you are plotting now this pressure versus this fixed temperature, then it is called isotherm. For fixed temperature, then it is called isotherm. What you are basically doing, you're trying to keep the temperature same and see what happens to the pressure. And then if you plot a graph, that graph is called as isotherm. Now the two state in this variables, state variables can be described in two ways, two types. They are called as extensive variables or intensive variables. These are the variables which will indicate the size of the system, which try to tell you how big the system is, the size of the system. So what do you think out of this can tell you the size? That would be obviously volume, mass, okay, volume, mass, which will tell you the size of the system. And you can keep them constant also if you want to. That normally don't change until and unless you try to change it. Because you know that mass of this will not change any substance. Whereas on the other side, here indicate size of the system. I forgot the word. They try to indicate the size of the system. Here, ulta it is. Do not indicate the size. The examples will be temperature. Temperature can never tell you how big the this substance is or the object is. Temperature, pressure. So this can change anytime. Variable that change. Okay, so the two types of variables are extensive and intensive. Extensive are the ones which try to indicate the size of the system, like volume, mass, and then they usually remain same. Intensive variables are the ones which do not indicate the size. So the examples will be temperature and pressure, and then they tend to change. Until and unless you try to forcefully keep it constant, they can change. Next are the thermodynamic processes. Okay. Before starting with the actual processes, we'll try to understand what is called as a quasi-static process. Then the main four ones we will see, two processes. Before that, we'll just say what is a quasi-static process. I told you last time, suppose if you have any system A, B, and it is what isolated from the surrounding, or if you are trying to put some adiabatic, something you are doing and you are trying to isolate it from the surrounding. Now what is going to happen? Their whatever variables will never change. This one's pressure, if you are putting at P1, V1, V2, V2, they might be at different this, but what is going to happen, as long as this wall is not removed, they will try to remain in their own state. If this is you are putting at 27 and if this you are putting maybe at 80, the temperatures will never change as long as that this is removed and put by a diathermic wall. Then only it will exchange will take place. But then it is said to be what? At thermo normal one. Okay. Thermodynamic equilibrium it would be. No change will happen till the conditions are changed. Now quasi-static process is something similar only, but it's called as a very slow process. Like consider if you are trying to put a hot tea in a thermoflask. Actually, you cannot keep it for 1 year. Okay, even if you like try to keep it for 1 year, it would change. No, the temperature will not remain the same. But if you check for 2 to 3 hours, you might get the same temperature, same pressure. What is happening is this is like a infinitely. This I'm just giving you a rough example. So that way there are processes that with time, with time, then later the temperature, the pressure might change. But for a very long time also, it is so slow that process, it is not losing any of its energy to the surrounding. For you, it looks like it is very constant only. That is called as infinitely slow process. It is so slow that you think that it is not changing at all. It's like constant only. The system changes its variables so slow like pressure, temperature, volume, so slow or so slowly that it almost remains thermal and mechanical equilibrium with its surrounding throughout. Okay, it may take some years for the pressure, volume, and temperature to change, but it is not like it will not change. But that process is so slow that you have to assume it to be like almost at equilibrium only. So that is called as a quasi-static process. Static means it's like same state, like in a statue form, static at the same place where it was. Okay, because the time taken for this to change is too big. Now the main ones which we have to know is the first one, isothermal process. So isothermal is at constant pressure. Just write the shortcuts and keep, or the basic ones and give. It's a thermodynamic process which occurs at constant pressure. Sorry, constant temperature. Second one is, if you see, isochoric. That happens at constant volume. Third one is, wait on, this is isochoric, yeah, correct. Then is isobaric. Isobaric, you can say, that is at constant pressure. Fourth one is adiabatic. Delta Q is 0. Yeah. Delta T is 0. Yeah. Delta V is 0. Yeah. Delta P is 0. Delta Q means adiabatic, you know what adiabatic means. It's a purely insulated system. In the previous class we had seen no heat change takes place. If you put anything inside a adiabatic, I told you heat doesn't go out nor heat comes in. So change in the heat will be 0. So no heat flow between system and the surrounding. There is no heat flow between system and the surrounding. So these are the four main processes, thermodynamic processes there. So first we start with isothermal. Process, or you can say thermodynamic process, which occurs at constant temperature. That is, temperature of system is kept fixed throughout. Volume and pressure will change. Best example of isothermal process is your refrigerator, your fridge. Okay, whatever it may be, some changes, something must be happening inside the system. Everything, all the external gas, whatever you're placing, even if you try to place some hot object inside this fridge, some process will take place, heat exchange, some compression, back to this pressure, gas, everything under the compressor. The main aim is, what happens is, the temperature of the refrigerator will remain constant. So the aim is to do that. if you are setting the refrigerator at 4 degrees Celsius, it will maintain at 4 degrees Celsius all the object whatever you are placing inside. But now this has to happen. It should be a very slow process. I mean, suppose if you have that same piston thing, and now you're putting some load on that, some pressure, and now you're supplying some heat. Imagine suddenly you supply heat. Now what is going to happen if you suddenly supply heat? Now your aim is to keep temperature constant. So quickly if you put it on fire, on a high fire suppose, what is going to happen? All this will become very hot, all this gas. So temperature will definitely rise. If it was 27, it would become 30 also based on this. Now the aim is, it's a very extremely slow process. I can say slow process, very slow, very slow process. Why? You have to provide very little heat at a time, so that what happens is these walls are conducting. Okay, and write this also, conducting walls it should have. So what is going to happen? Very small heat. So what is this heat will directly pass through this wall, and the work, whatever energy, small energy which are supplying to the system is gone in trying to push this piston up, because there is some load put here. So now there were two options for this fire or for this heat. That one is to increase the heat of this temperature of the gas, or to do the work of lifting up the piston. So that small heat is not sufficient enough to increase the internal energy. Whatever you're supplying is going to raise the this, what is that, work, or that piston. The gas will expand and it will try to push the piston up. So there is no time or no enough energy for this one to rise its temperature. So whatever you're supplying should go in doing the work and not to rise the temperature. That is why it has to maintain a constant temperature. So that's why it's a very slow process. And I think transfer of heat into or out of the system happens slowly, so that thermal equilibrium is maintained. Thermal equilibrium means temperature is maintained, I can say. So that constant temperature, the thermal only, the words which is there. So that thermal equilibrium is maintained. Example, the refrigerator. Okay, some changes, a set of changes might take place in the mechanism, but the temperature inside will always remain constant. What is happening? The heat is removed from the refrigerator and given out to the surrounding. But that is, it's a slow process. So you will not see like you are putting in some substance and within seconds it will become cold. It will take time. Now under isothermal process, we'll see what happens for ideal gas. Under isothermal process, Vandya, we know that it's a constant temperature. Therefore, delta T is 0. For ideal gas, P is always proportional to 1. Or you can say PV is always constant for ideal gas. So even if some changes take place, no? So what is going to happen? For ideal gas, PV is always constant. Your temperature total, okay, P into V will be constant. Your temperature will definitely not change of the system. So after some time, this system, okay, this temperature will remain same. Maybe it had P1, V1, this had P2, V2. Pressure and volume will change in order to maintain the temperature same, because it has to maintain constant temperature. What can change? Pressure and volume might change. So this is for some time. After some time, it will be this. But as for ideal gas, this has to be remain constant. So we know that P1, V1 will be equal to P2, V2 for ideal gas. Overall, okay, pressure and volume. Product of pressure and volume will also be same. We'll see what happens to the internal energy. Isothermic process. Internal energy will be, I've used the same previous formula only of internal energy, mu Cv delta T at constant volume. If you are using 1 mole of gas, no, then this will go. We had already proved, no, this thing. Equation 1 or 2, I think, under the relation between Cv and Cp, no, under that we had seen that Cv is delta U upon delta T, because this 1 molar we have taken constant. This at volume, this molar we have taken 1. Even if you don't take this, it's fine. So what is going to happen? Delta T is 0 for isothermic process. Internal energy for of a ideal gas for isothermic process is always 0. So if internal energy is 0, what will be the heat supply? First law of thermodynamics. You know, delta Q is nothing but work done if delta U is 0, and it is heat supplied is directly used as work done. We have seen this also, I explained to you all. What I told you, whenever you're supplying the heat, the whole thing is done what to lift the piston up. Okay, this whatever slow energy what you're supplying is used to lift the piston up, not to heat up the molecules. If the volume, this molecules get heated up, its temperature will rise. But for isothermic, you have to keep temperature same. So whatever heat will go to rise the temperature. So heat supply is directly equal to the work done. Internal energy, no work, no increase in that. So that's why that would be 0. Internal energy is 0 and heat supplied is equals to work done for ideal gas under isothermic process. This is for ideal gas, okay? Now in general we will see. You can write and give in your own words. Heat supplied you can say slow heat supply is used only to do work on the, that is to raise the piston and not on internal energy. Now we will calculate how much is the work done. This is the derivation. Work done for isothermic process. Because we have one more derivation, work done for adiabatic also. Suppose just consider an ideal gas. Consider ideal gas. Which goes isothermically from initial state there might be P1 V1 to final state P2 V2. Means what? I had a piston, I gave some heat, slowly its work was to raise the piston. It did its work without changing the temperature. But now if you notice this has rise. So what is going to happen? Pressure must have changed, volume also has changed of the piston. So here it must be P1 V1, this must have become P2 V2, temperature keeping constant. So consider an ideal gas which has undergone from this stage to this stage. So we'll consider one middle stage. Consider any intermediate state with pressure P and volume change from V to delta V. We know that work done This is the formula delta V. Delta W is P. Work in terms of this also we have seen P into delta V. Work in terms of pressure and volume. For very small work done or for very small volume change. So extremely small, like in pieces, we will check. Extremely small pieces, like very small change. So that we'll consider dW. In this, we'll consider dV. So dW will be equals to P d. This is for a small one. Now overall, if you want, okay, so therefore total work done, you have to integrate it. Means you have to add up all these strips. This is like dW. Again dW. So total is nothing but integration. So integrate. This is from V1 to V2. Initial to final. Anyway, this one with respect to dW will be W. Because you know that integral of 1 dx is x. 1 with respect to that letter, no, it always becomes a normal letter. If you had like 1 dt, it would become t. That's why if you have 1 dw, you'll get w. Now p is a constant. The constant, so it will come out of the integral. So what remains is 1 dv. So 1 with respect to dv, 1 with respect to dw was w. So 1 with respect to dv will be v. When you write the answer, the integral sign goes. This is from v1 to v2. Always higher limit minus lower limit. This will keep 1 second. Constant volume if we keep, pressure if we keep constant. 1 second. This pressure will not be considered. Pressure is also changing now. We have written 1 second. Pressure has also changed from P1 to P2. You cannot consider this condition. Just till here you erase it. If we keep pressure constant, then we cannot take this. We have already said P1 is changing from P2 V2. Pressure is changing, so we cannot assume constant and remove it out. So we'll have to think something. 1 second. P, no? So ideal gas we might have to think. So I'll have to express. We cannot integrate directly. This is a variable. Suppose now this is changing. Okay. Now this we cannot integrate with respect to V. If this is P, this has to be also P. Now if this has, if we want to integrate, we have to express pressure in terms of volume now, because both have to be in terms of V. And this we cannot remove out. because it's a variable, it is changing. So what we'll have to do is try to express P in terms of V. So we know ideal gas is mu RT. So P I'll try to find. Now these are constants. Why? Temperature is constant for isothermic. We have already assumed temperature is constant. Pressure is not constant. Pressure and volume is changing. So I'll put this here. So this anyways will become right like this. V1 to V2 mu RT upon V D. Now these three constants I'll remove out because mu is a molar number, pure number. R is also gas constant. Temperature is also constant. And now it will be fine. Now this is out. Integral of 1 with respect to the W is W, work. These are your normal integration formula. 1 dx is always x. Integral of 1 by x is always log x or ln of x. Log of x, natural log. So mu RT, this is 1 by V. So it will be ln of V from V1 to V2. This integration is in detail in 12th standard. Actually, this whole system one is wrong. Integration should have been done first and then only this concept should be introduced. Because it's difficult to understand them when you don't have the basics of integration. So mu RT, this we have to substitute always higher limit minus lower limit. If a 12th standard student who already knows now integration is asked to solve this, they'll finish in 10 seconds. Because it is that simple once you know the concepts of integration. Again, there's a formula. Wait on. Log A minus log B is log of A upon B. If it was multiplication, this plus, it gets multiplied. Log A plus log B is log A into B. And if it's minus, then they get divided. So as per them, this will go to the denominator. V2 upon V1 you will get. If I want to remove natural log and convert it into normal logs, then the value is 2.303 log x. So the final answer is, I'll remove this ln and write it as log of V2 upon V1. So this is the work done for isothermic process. Isothermal process. So if V1, V2 upon V1, no? So if V2 is greater than V1, then work is positive. If V1 is greater than V2, then work is negative. Volume means what? Final volume is more than the initial, means what has happened? This is called expansion, no? Volume has increased, final. Now initially, what has happened? Same signs are given, beta. This is V2 less than V1. This is called compression. Final volume has reduced, suppose. That means it is compression. Then the work done is negative. So for expansion, work is positive, and for compression, work is here positive expansion, and for compression it is negative. Okay, so this is all about isothermal process. So I'll stop here. Next class I'll do the remaining 3.